Hi folks, and welcome back to Educator.com. What I'd like to do now is take a few minutes to go through a review of some of the math skills we're going to need to be successful in this course. So, our outline. We're going to talk about the metric system and the System International, or SI units, the unit system that we use here in physics. We'll talk about significant figures, scientific notation, and finally the difference between accuracy and precision and why they're so important. So, objectives: convert and estimate SI units. Recognize fundamental and derived units. Express numeric quantities with correct significant figures so we understand how accurate, how precise our measurements are going to be. Use scientific notation to express physical values efficiently. And finally, differentiate between accuracy and precision. So, why do we need units? Well, physics involves the study, prediction, and analysis of real-world events. And real-world events have quantifiable numbers. In order to communicate these to other people accurately, we need to have some sort of standards. Whether the sound was this loud or this quiet. We need to put a number on that so we can communicate to people. The light was this bright or this dim. How do we put numbers around that? We have to decide on a set of standards, and physicists have agreed to use what's known as the System International, which is a subset of the metric system. You'll also sometimes see it referred to as the MKS system because the basic units include meters, kilograms, and, for time, seconds. So let's talk about it. The System International is comprised of 7 fundamental units. It's based on powers of 10, because it's a subset of the metric system, and all other units are derived from these basic 7. The fundamental units are the meter, the kilogram, the second, hence the MKS system, the ampere, the candela, Kelvin, and a mole, which you may be familiar with from chemistry. So let's start with the meter. The meter is a measure of length, similar to a yard in the English system. For measurements smaller than a meter, use a centimeter, about the width of your pinky finger perhaps, millimeter, 1/10 of that, micrometer or micrometer, which is oftentimes written μm, and the nanometer, nm. For measurements larger than a meter, typically we use kilometers, kilometers, 1,000 meters. The kilogram, on the other hand, is roughly equivalent to 2.2 English pounds. For measurements smaller than a kilogram, we oftentimes use grams or milligrams. A gram is about a paperclip. For measurements larger than a kilogram, we could use things like a megagram, also known as a metric ton. That's 1,000 kilograms. And time, everyone's probably familiar with this one. The base unit of time is a second. And unlike the rest of the metric system, time's a little funny. It's not based on units of 10. We have instead things like minutes, which is 60 seconds, hours, which is 60 minutes, days, which is 24 hours, years, 365 1/4 days. But most of us are so familiar with this, that's not really a big deal. For shorter times, we go back to base 10, things like milliseconds, microseconds, nanoseconds, and so on. All right, we can take and we can make other units from these fundamental units. A unit of velocity or speed, for example, is a meter per second. What I'm going to do is I'm trying to convert to kilometers, K. So I go over here to my table of prefixes, I find K, kilo, and I see that it means 10 to the third. So I'm going to write 10 to the third over here on the bottom, because on the bottom there's no prefix in front of my unit. If I put 10 to the third here, I'm going to put 1 on the other side. What I've now made is a ratio 1 kilometer over 10 to the third meters. And 1 kilometer is 1,000 or 10 to the third meters. What I've really written here is 1, but I've written it in a special way so that when I multiply this through, my meters make a ratio of 1. 2,480 times 1 kilometer divided by 10 to the third is going to leave me with 2.48, and my units that are left are kilometers. 2,480 meters is 2.48 kilometers. Nice, simple way of converting units. Let's try another one. 5.357 kilograms, let's convert that to grams. I start by writing what I have, 5.357 kilograms, and I write it as a ratio over 1 times, well, I want kilograms to go away, so I'll put kilograms in the denominator. I want grams in the numerator. Now I go down to my prefix table. I look up kilo. Kilo, K again, is 10 to the third. I'm going to write that on the side that does not have a prefix. So that goes in the top this time. I put a 1 in the bottom. Now, kilograms and kilograms make a ratio of 1 or cancel out. What I'm left with is 5.357 times 10 to the third grams divided by 1. So 5.357 times 10 to the third is just going to be 5,357 grams. There we go, converting fundamental units. Let's take a look at a two-step conversion. Sometimes you might have to do this in a couple different steps. If we want to convert 6.4 times 10 to the minus 6 milliseconds to nanoseconds, I start by writing what I have, 6.4 my answer. Exactly as we expected. All right, let's do one with some derived units. We have 32 meters per second, and we want to convert that to something like kilometers per hour. Well, we're going to follow the same basic path again. I'm going to write 32 meters per second as a fraction. And if I want to convert to kilometers per hour, I can convert either the meters or seconds first. Doesn't much matter. Let's start by converting the meters to kilometers. So I want meters to go away, that goes in the denominator, and I want kilometers in the numerator. I go to my handy-dandy table over here, and I find that kilo means 10 to the third. That goes on the side without a prefix, and 1 goes on the other side. Now I'm going to be left with kilometers per second, but I want kilometers per hour. So I have another step. Seconds here in the denominator, I need those to go away. So I put seconds up here, and it'd be nice to put hours down here, but I don't really know how many seconds are in an hour. But I know how many seconds are in a minute. So I'll do this first. I'll say there are 60 seconds in 1 minute. Now when I look at my units, my seconds will cancel out, and I'm down to kilometers per minute. I'd best do another step here. So if I want minutes to go away, I'll put that in the numerator. I want hours, and I know that there are 60 minutes in 1 hour. I check my units again. Minutes make a ratio of 1. And what I should be left with for units is going to be kilometers in the numerator per hour. I'm all set to go do my math. 32 times 60 divided by 10 to the third should give me about 115.2 kilometers per hour. A derived unit conversion problem. Let's take a look at a multi-step conversion. One last unit conversion problem. Let's see how many seconds are in 1 year. I have no idea, but it's kind of a fun problem to take a look at. Let's start with 1 year. We'll make that as a ratio. And I don't know how many seconds are in a year, but what I do know is that there are 365¼ days in 1 year. Years make a ratio of 1, and I'm left with units of days. Okay, still not to seconds. So I happen to know that if days go away, I know that there are 24 hours in 1 day. All right, days will make a ratio of 1, and I'm down to hours. Still not to seconds. So another step, I want hours to go away. I'll convert to minutes. I know there are 60 minutes in 1 hour. Hours will make a ratio of 1, and my units are minutes. We're getting closer. I want minutes to go away, so I'll put minutes in the denominator. I want seconds, and there are 60 seconds in 1 minute. Minutes will make a ratio of 1, and I'm left with my units of seconds. So when I go through and I do all this math, 1 times 365¼ times 24 times 60 times 60, I come out with about 3.16 times 10 to the 7th seconds. That's a lot of seconds in 1 year. Another useful tool or skill is being able to estimate some of these units. For example, estimate the length of a football field. Well, that's pretty big. Just a rough ballpark figure, maybe about 100 meters. If you're familiar with the English system, 100 yards, 100 meters, roughly the same thing. Or the mass of a student, maybe 60, 70 kilograms for a typical student. Length of a marathon, somewhere in the ballpark of about 40, 42 kilometers. Or the mass of a paperclip, I think we mentioned this one previously, somewhere in the ballpark of about 1 gram. So as you walk around, see different objects, see if you can't take an estimate of what their mass, their length, their time is in various units. A useful skill. So now let's talk about significant figures. Significant figures represent a manner of showing which digits in a number you know to some level of certainty. For example, if you're walking along and you see a garden gnome in somebody's yard, significant figures can help you understand to what exactness you know the height of that garden gnome. 14 centimeters? 14.3827482 blah 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 centimeters, or 14.0 centimeters? These three numbers are all telling you slightly different things. What do they mean? Sizes. For example, when we talk about length, we could talk about something like the width of a country like the United States, probably a pretty big number. But we also have to talk about something like the thickness of a human hair, all with the same base measurement, meters. Or even smaller, how about the transistor on an integrated circuit, where those are getting so small that it's smaller than the wavelength of light, so small that there is no optical microscope in the world that can ever see some of those features. Huge ranges in orders of magnitude for these different measurements. Scientific notation can help us express these efficiently and make it much more easy to read. For example, which of these numbers is easy to read? 4,000,000,000,000,000,000,000, or 4 times 10 to the 12th? Well, that's obvious. That's a lot easier to read and much less chance of making a mistake. Or, which is easier here? 0.000000001 meter, or 1 times 10 to the minus 9 meter. I think it's easy to see that those are a lot more accurate and less error prone. It's almost tough to read these numbers with all the zeros because it's so easy to lose your place in them. So using scientific notation, first off, show your value using the correct number of significant figures. Then move the decimal point so that only one sig fig is to the left of the decimal point. Finally, show your number being multiplied by 10 to the appropriate power so that you get the same quantity, the same numerical value. And finally, let's talk about accuracy and precision. There's a difference between these two, and in everyday speech we oftentimes use them interchangeably, but in the world of physics and science, there's an important distinction. Accuracy is how close a measurement is to the target value. Precision, on the other hand, is how repeatable your measurements are. And I like to look at these from the metaphor of target practice with the bow and arrow. If we're aiming over here toward our first target, and we're kind of all over the place here with our arrows, and by the way, they're nowhere close to the target and they're nowhere close to each other, we have low accuracy and low precision. Typically not what you're after. Over here, however, we have pretty high accuracy. We're starting to get pretty close to the target, but we're still not repeatable. We're accurate, close to the target, not repeatable, therefore we have high accuracy and low precision. All right, over here, we're nowhere close to the target, but man, we can hit that same spot nowhere close to the target every time. We are extremely precise, but our accuracy is off. High precision, low accuracy. And finally, the nirvana of measurement. We have high accuracy, we're very near the target, and we're repeatable. We have high precision. We can get near the target, and we can get near the target every time. All right, so with that, let's take a look at a couple more examples. Let's show this number, 300 million, in terms of scientific notation, assuming we know 3 sig figs. Well, if I know 3 significant figures, and I want to show this in scientific notation, I have one number, one digit to the left of the decimal place, and I know 2 more sig figs, so I'd write that as 3.00 to give me my 3 sig figs, and then I multiply it by 10 to the appropriate power, which would be 1, 2, 3, 4, 5, 6, 7, 8. 3.00 times 10 to the 8th. How about showing this number, 0.000000, there's no way I can read that whole thing, 282 in scientific notation? Well, we have 3 significant figures, so this must be 2.82 times 10 to some power. What power is that going to be? Well, we got to move the decimal place 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 places to the right. So that's 10 to the minus 15. Man, isn't that a lot more efficient and easier to read? How about here? Express the number 0.000470 in scientific notation. All right, well, we've got 3 significant figures, so 4.70 times 10 to the, and the power is going to be 1, 2, 3, 4 to the right, so 10 to the negative 4. And one last one. Let's see if we can't expand 1.11 times 10 to the 7th. So we have 1.11, and we need to move the decimal place 7. So 1, 2, 3, 4, 5, 6, 7. So I would write that as 11,100,000. 11,100,000. Hopefully this gets you a good start on some of the basic math skills we're going to need here in physics, especially around scientific notation, significant figures, units, converting units, and accuracy and precision. Thanks for watching Educator.com. We'll see you next time, and make it a great day.